Good morning, everyone. It's Miss Meneely, and I want to apologize that I sound like I'm speaking in an auditorium. I'm not sure what's wrong with my microphone, and I'm sorry I can't be here today. I am going to go ahead and continue our lesson on binomial probabilities, and today I'm going to show you actually how you can use your calculator to calculate those probabilities instead of working it all out by hand, and I know that's kind of a nuisance. So at this point, you should have completed your warm-up. I'm going to go through those answers pretty quickly. And then we're going to talk about, again, the conditions for using a binomial random variable and then computing the probabilities. We'll also talk about computing the mean and standard deviation of a binomial random variable. And they're easy formulas, so that's going to take a few minutes. Okay, in number 1 of your warm-up, it says to determine whether or not each of the following situations can be described by a binomial distribution. This is just like your homework. So if it can, you want to also identify the values of n and p. So in part A, it says, based on information from USA Today, 70% of people over 35 years of age prefer Christmas vacation in a warm, sunny climate. A random sample of 42 college students was asked where they would prefer to spend their Christmas vacation. And so in this case, if we take a look at our successes versus failures, we could say that success is equal to whether or not they prefer a warm climate. So I'm just going to say perform warm or prefer warm, and failure would obviously be something else. In terms of our number of trials, we're looking at 42 college students, so my n would be 42. I can assume independence. It's not stated in the problem, so you want to make sure that you actually write the word assume independence. And that may or may not be true. I mean, if you're talking about people that know each other and you're dealing with a situation where, you know, one's going to go to warmer climate if someone else does, then we wouldn't be able to assume independence. But in this case, since it's a random sample, it's fair to assume independence. And we can also assume that the population of college students is large enough that even though we're sampling without replacement, that we still have independence. Now, when it comes to the probability of success, this is where we need to be a little bit careful. In the problem, it says that 70% of people over the age of 35 years of age prefer Christmas vacation in a warm, sunny climate, and yet we're asking college students. So we can assume that the probability of a college student choosing a warm location is going to be constant, but we don't know what that value is. So what we can say here is that p is unknown, but we can assume that it's constant. And so even though it's not given to us, this situation still meets the binomial criteria. And basically what I would say is if x represents the number of students, you know, preferring a warm climate, I would say that x is distributed binomially. I know the value of n is 42, but I don't know the value of p. So I would just say p is unknown. But it still meets the criteria. All right. In letter B, it says Harper's Index reports that nationally only 14% of all home burglaries are solved. A random sample of 300 burglaries is selected for observation. Okay, so again, a success in this case would be a burglary. I'm just going to abbreviate. So a failure would be no burglary. Okay, we have a sample of 300, so I know that I have a fixed number of trials. I can assume independence because our population is going to be very large, and we also have a random sample. And then in terms of the probability of success, we know that it is 14%, and we can assume that that is constant. Since all our conditions are met, if x represents the number of burglaries, then I can say x is distributed binomially with an n value of 300 and a p of 0.14. And again, you also need to make sure that you remember to define your variable if it's not defined for you in the problem. Okay. In letter C, it says James Burke in his book's Chances, Risk and Odds in Everyday Life, he states that only 6% of all people worth over $1 million inherited their wealth. A random sample of 250 millionaires is selected. So a success in this case wouldn't be a millionaire, it would be whether or not they inherited their wealth. And then failure would be they did not inherit. Okay, we're sampling 250 millionaires, so N is 250. Because it's a random sample and I know my population of millionaires is going to be a lot more than 250, I can assume independence. Okay, the probability of success, the probability that someone inherited their wealth, we are told is 6%, and I can assume that that is constant. Since all of my conditions are met, I would say X represents the number who inherited their wealth, and X would be distributed binomially. My N value we said is 250, and my P is 0.06. Okay. And the last one, Steve and Kathy guide climbing parties up Long's Peak. They say that when the weather is good, the probability of reaching the summit without having to turn around for some reason is 80%. But when the weather is not so good, the probability is 50%. Next week, Steve and Kathy have 20 guided climbs scheduled. So a success in this case would be reaching the summit. Failure would obviously mean not. We've got 20 guided climbs, so N is 20. And I can assume independence between the climbs. I don't think one climb is going to affect another climb. Oops, independence. I don't know why that's such a hard word for me to spell. But here, if I think about the probability of success, it's not constant. It depends on the weather. So when we're talking about independence, we're talking about the independence between climbs. And one climb is not going to affect the other. The climbs are affected by the weather, and that's why the weather changes. Or I'm sorry, that's why the probability changes. So even though we have independence, our probability of success is not constant. And so in this case, it's not binomial. All right. And then in the second question, it says on a roulette wheel, there are 18 black numbers, 18 red numbers, and 2 green numbers. Suppose you're interested in placing bets on black, and you will play the wheel 3 times. If X represents the number of times the wheel lands on black, X has a binomial distribution. So the values of N and P. So we're going to play 3 times. So in this case, N is 3. And my probability of success, if success means that it lands on black, I know I've got 18 numbers that are black, and there are a total of, if we add 18 and 18, we get 36. Add another 2, that gives us 38. So our probability of landing on black is 18 out of 38. It says, how many ways can the wheel land on black 2 times? So remember, this is the binomial coefficient. So basically, I'm trying to figure out I'm doing it 3 spins, and I want to choose black twice. So that's one way of writing it. We said another way of writing that would be to do 3, or N choose K, or 3 choose 2 this way. If we're doing this by hand, we would take our N value, factorial, and put that on top. And then on the bottom, we'd have our number of successes, factorial, times the number of failures, factorial. And so the 2 numbers on the bottom should add up to our N value. The fastest way to compute this, though, is to use this option on your calculator. And so if we go over to math and select probability, actually the first thing you want to do is type in your N value, sorry. So if I type in my 3 first and then go to math, probability, and I'm going to choose option 3, and then I'm going to type in 2. And that tells me that there are 3 ways that I could have 2 successes or land on black twice. So if I wanted to determine the probability that X equals 1, that means I have 1 success. And so I'm going to have 3 spins. I'm choosing 1 success. I want to multiply that times my probability of success, which we know is 18 out of 38. And I have 1 success. So then I want to think about my probability of failure. So that would be 20 out of 38. And in this case, I'd have to have 2 failures. And so I could actually just multiply or continue I do second enter, sorry, I'm not speaking very clearly, and I'm just going to change the 2 to a 1, and that tells me that there's 3 ways that I could have one success or land on black once, and then I want to multiply that times 18 over 38 to the first power, which I'm not really going to worry about, times 20 out of 38, and I want to square that. And if I press enter, this is the probability of landing on black twice. All right, so let's go ahead and talk about today's lesson. We're going to do a quick review of what we talked about last class in terms of the binomial setting. And as you've seen, obviously, using the formula to calculate binomial probabilities is really tedious, especially if you're looking at an inequality where you have to add multiple probabilities together. So I'm going to show you how to do this on your calculator. Make sure that you always, no matter what, define your random variable, which is always going to be the number of successes, and you just want to make sure that you define what a success is. And then you want to talk about your distribution. So you want to make sure you state that it's binomial and then identify the parameters. So anytime I ask you to use proper statistical notation, this is what you should be expressing. Okay. And so when we're performing the calculations, you need to make sure that you show your work. So you either need to make sure that you are stating the binomial formula or you're using the probability commands on the graphing calculator. Now, on the AP exam, you're not going to get credit for writing the commands the way they would be expressed on the calculator. So you want to make sure that you are showing as much work as you can. So, and then answer the question, obviously. So if we're given a discrete random variable x, the probability distribution function assigns a probability to each value. So the probability distribution function, that is your PDF. And remember, when we were dealing with a normal distribution, we never used the normal PDF because it's only used with graphing. So remember, we have continuous random variables and we have discrete random variables. Okay, so anytime I'm asking for something like the probability that x equals a number, this is considered a PDF, the probability distribution function. Anytime I'm looking for an inequality like x is less than 3, this is considered a CDF. Okay, and with a continuous distribution, we know that the probability that x equals anything is just 0. So we don't even bother with that. We just know that it's going to equal 0. But all of the other commands are going to be very similar. With the normal distribution, we were able to enter a lower bound and an upper bound, which made calculating the probability between two values very simple. Unfortunately, with the binomial PDF or the binomial distribution, it's not quite that simple. And I don't know why the calculator isn't consistent in how it asks for the parameters, but unfortunately it's not. So let's start with the PDF. So if I want to know the probability of exactly so many successes, so the probability that x is 3 successes or x is 5 successes, I can use this command on the calculator. And so notice the order of things. N is our number of trials. P is our probability of success. And then K is the number of successes that we're interested in. Okay. Now this command, if you remember, was on the distribution menu. So if you hit second vars, that's our distribution menu. And if you scroll down, remember we were always using either the normal CDF or the inverse normal. So what we want to do is scroll down. We'll actually be using all of these formulas at some point in this class. But if we scroll down, there's our binomial PDF. So suppose I wanted to go back to the question from our warm-up. Let's take a look at that question again. Where we were looking at the probability that x equals 1 success out of 3. So if I do the binomial PDF formula, the first thing I need to enter, and notice that on the new calculators, it's all prompted for you. So the number of trials in this case is 3. Our probability of success, and I'm just going to enter in the fraction 18 divided by 38. And then the x value, this again is our number of successes. In this case, we were just looking for 1. And so if I press enter, I should get the same thing that we calculated by hand. Okay. If you have one of the older calculators, though, when you enter the command, notice how it's written on the calculator. After you submit all, like after you've entered all the values into the menu and pressed enter, it comes up with this command right here. So if you have an older calculator, you do need to remember the order in which you enter the values. So it's always N and then P, and then the value of the number of successes you're looking for. And you're only going to use the PDF formula when you're looking for the probability that X equals something. So this is just a generic example where you have X is distributed binomially. Remember, the first number represents your N value, and the second number represents your P value. What I'd like you to do is pause the video for a minute and to go ahead and complete the probability distribution. So if I'm looking for X equals 0, I'm looking for the probability that X equals 0. Okay, so go ahead and pause the video. Okay, so the answers are now displayed. I'll just review one. So if I wanted to find, for example, the probability that X equals 0, I'm going to go back into my distribution menu. I'm going to choose my binomial PDF. And I'm just scrolling down, and there is a letter associated with it. So it's letter A, so you could also do alpha A, and it'll jump right to that command. In this case, we've got 4 trials. My probability of success is 20%. Make sure that you enter the probability, though, as a decimal. So if it was written as 20% this way, you want to make sure you change it to a decimal. All right, my X value, if I'm looking for the probability that X equals 0, I'm just going to type in a 0. And so we get 0.4096. And then you do that for each of them. Okay, so let's talk about what would happen if I wanted to find, for example, the probability that X is, say, greater than 2. I know that that would be equivalent to doing the probability that X equals 3 plus the probability that X equals 4. But even with the PDF command, that's going to be tedious, and we need to really be careful about rounding errors. So once you're given an inequality, we can switch to the CDF formula. So if you're given a discrete random variable, the cumulative distribution function, that's our CDF, basically is going to calculate the sum of the probabilities from 0 up to the value of X to determine the total probability of getting X or fewer successes among N trials. So the formula on our calculator is only good when we're looking at less than or equal to. So we'd use the binomial CDF. So for example, if I'm dealing with X and it's distributed binomially, and let me just say there are 5 trials, and let's do 0.3 as our probability of success. If I want to find the probability that X is, let's just do less than or equal to 2, then I'm going to need to enter in my N and then my P, and then my upper bound. So K in this case is going to be your upper bound of successes. You don't need to enter a lower bound. Remember with the normal distribution how you had to go from like negative 9999999 to your upper bound? That's what makes the rest of these functions a little annoying, because they're not modeled the same way the normal distribution function is. So we don't have to worry about a lower or an upper bound. The binomial CDF is always talking about less than or equal to. So in this case, I'm going to go back to my menu. So I'm going to do the second distribution. The binomial CDF, I believe, is just alpha B, and that'll take you, if you look up at the top of the screen, it should say binomial CDF. You could also just scroll down, which is kind of annoying. And then you're going to plug in the values just like we did before. So my N value is 5. My probability of success is 0.3. And because I'm doing less than or equal to 2, my X value is going to be that upper bound of 2. And so if I paste that all in, I get a value of 0.8369. Okay. But what about if I wanted to do the probability that X is less than 4? Okay. I have to be careful here because my calculator requires me to put in the upper bound. So let's just kind of look at a number line. I know that's kind of silly, but if I'm thinking less than 4, remember this is a discrete random variable, so I can't have any values between 3 and 4. So less than 4 is going to be equivalent to less than or equal to 3. And once I have it in the terms or in the form of less than or equal to, I can do my binomial CDF again. So I'm going to go back into my distribution menu. It's alpha B. That should drop me right to the binomial CDF. I have my number of trials is 5. My probability of success is 0.3. And my upper x value, my upper bound, even though I'm trying to find the probability that x is less than 4, that's equivalent to being less than or equal to 3. So 3 is my actual upper bound. And when I paste, let's see, we're going to get 0.9692. Okay. But what about if I wanted to find the probability that x is, say, greater than 1? So let's look at my number line again. And I'll just use a green pen, so ignore the blue that I have on there. So if I'm looking for greater than 1, that means it could be a 2, a 3, a 4, or a 5. That's the same thing as leaving out the values of 0 and 1. So that would be the same thing as doing 1 minus the probability that x is less than or equal to 1. So if I flip this, the complement of this would be 1 minus the probability that x is less than or equal to 1. And so now I'm just going to have to add 1 minus to the front of my probability command. So now I'll go into the second distribution. I'll choose my alpha B. The 5 and the 0.3 are the same, but this time my upper bound is going to be 1. Okay, and so the 1 is already in there, the 1 minus, and we get 0.4718. Okay, so that one's a little bit tricky. If I had the probability that x, if I was trying to find, for example, the probability that x is greater than or equal to 4, that would be the same as 1 minus the probability. So if I think about greater than or equal to, I'm talking about these two outcomes. So if I want the complement, I'm looking at 3 or less. So this would turn into the probability that x is less than or equal to 3. So it is a little bit confusing to do the flip. So if drawing a number line will help you in any way, I would definitely encourage you to do that. All right, so you have several examples, problems 2, 3, and 4, that I'd like you to go ahead and complete. I'm going to pause. I'd like you to pause and take a few minutes to do that. Hopefully it won't take more than about maybe 10 minutes to complete those problems. And then I'm going to explain to you how to calculate the mean and the standard deviation. So please go ahead and press pause. Okay, so let's go ahead and take a look at the answers to number 2. The first two are, I think, pretty straightforward. In letter C, where you're asked to do the probability that x is greater than 3, think about the complement would have to be less than or equal to 3. And again, that makes it a little bit easier to enter in. We're still doing the 1 minus, but we don't have to translate that x is less than or equal to 3. We do have to be careful about letter D, though. If we have x is greater than or equal to 3, the complement would be everything that's just less than 3. So if you write it like that first and then interpret that less than 3 is equivalent to less than or equal to 2, it might help you in rewriting that expression to calculate the probability a little bit easier. In number 3, you're given another binomial distribution. We're talking about the number of made baskets out of 12. So n is the 12 baskets. The probability of making the basket is 75%. So in letter A, we're asked to find the probability of making exactly 7 shots. And then in letter B, it means at most. So 7 would be the maximum number of shots that this person could make. The reason these two probabilities are different, they both include exactly 7 shots. But in letter B, it also includes the possibility of getting 1, 2, 3, 4, 5, or 6 made baskets. So the probability in part B should be higher because it includes other likelihoods. And then finally, in number 4, this is again a binomial distribution. This is similar to the example that we looked at last class. We've got n as our 10 switches that we're sampling, and our probability of success is 10%. And remember, because we know that the shipment is so large, we don't have to worry about independence. We've got it. Okay, and so the ones that are a little bit tricky would be these last two. And so again, when I look at x is greater than 3, when I take the complement of that, I'm looking at x is less than or equal to 3. And the complement of x is greater than or equal to 6 is going to be 1 minus the probability that x is less than 6, which is the same thing as x being less than or equal to 5. Okay, the last thing I want to show you is how to calculate the mean and the standard deviation of a binomial distribution. It's really, really simple. Our expected value is simply going to be, and remember, mean is the same thing as expected value. Our expected value is just going to be the product of our number of trials times the probability of success. If you think about it, let's say I toss a coin 10 times, and I know that the probability of getting heads is going to be 0.5. So if I toss a coin 10 times, what is the expected number of heads that I would get? The answer is 5. You can do that intuitively. The easiest way to calculate it, though, for any binomial distribution is just to multiply n times p. The standard deviation is just going to be the square root of n times p times 1 minus p. And remember, p is our probability of success, and 1 minus p is just our probability of failure. Okay, and these formulas are really good when we're trying to describe a distribution of a binomial function. So remember, when we think about like shape, center, and spread, these are our values for center. This is how we would calculate the spread, and we'll talk about shape a little bit later. Okay, so you're given two examples. I'll do the one with you. It says the count x of bad switches is known with a binomial distribution where n is 10 and p is 0.1. This is the sampling distribution the engineer would see if she drew all possible simple random samples of 10 switches from the shipment and recorded the value of x. We want to determine the mean and the standard deviation. So my mean of x, remember, is just n times p, which in this case is going to be 10 times 0.1, or 1. And you want to make sure that you also identify what we're talking about. I guess that would be one bad switch. And then my standard deviation is just going to be the square root of n times p times 1 minus p, or the square root of 10 times 0.1 times 0.9. And that ends up being 0.9487 bad switches. So if you're asked to interpret, I would say in a sample of 10 switches, I would expect 1 to be bad, and that value would vary by about 0.949 bad switches. Okay? So let's go ahead and do number 6. I'll go ahead and pause. Okay. In number 6, we know that 60% of all buyers of new cars choose automatic transmissions. For a group of 5 buyers of new cars, calculate the mean and standard deviation for the number of buyers choosing the automatic transmission. So in this case, a success would be buying the automatic. So x represents the number who buy the automatic. So remember, you always want to define your random variable. In number 5, that was defined for us. Okay, and it really is important that you define your random variable, because I may look at number 5, for example, and call a success a bad switch, where someone else might decide to call a success a good switch and then flip the problem. So you do want to make sure that you're being consistent in how you're interpreting the problem, so you do want to make sure you define your random variable. All right, so in number 6, we know that we're choosing 5. We know 60% of buyers choose new cars. I can assume the independence, so I know I have a binomial distribution. So the mean would be 5 times 0.6, or 3 buyers of automatic transmission. The standard deviation would just be the square root of 5 times 0.6 times 0.4, and that's going to be 1.095 buyers. All right, so again, you're going to use the binomial PDF if you have to calculate the probability that x equals anything, and you'll use a CDF if you're trying to find the probability that x is less than or equal to any number. So as your wrap-up, what I'd like you to do is just add on whatever you need to your study guide, and then complete problem number 1 on the back of the paper, because now you can use the calculator to determine those binomial probabilities. I'd like for the sub to go ahead and pass out your homework. You can go ahead and get started if there's time. Otherwise, make sure you finish it for homework. Have a great day, guys. I'll see you next class.